So we're going to switch gears today, or for this talk. We're still going to be looking at tabular MDPs, but we're going to be looking at instance-dependent guarantees, which I'll get to in a moment. So typical setup that we've been seeing this morning, aside from the last talk, finite horizon, tabular MDPs, finite states, finite actions. Agent takes an action, reaches a reward, evolves to a new state. You're going to assume that the transitions and the rewards are unknown before the start of the game. One deviation from Shipperstock is we're going to consider a finite collection of policies pi, big pi, and this can be an arbitrary set. Okay, it can be all stationary policies. It can be an arbitrary collection of a few policies. You could think of this as being like an A/B testing sort of thing, where you're going to deploy some policies on Uber's network of assigning drivers to cars and things like this. And it's just policies came from out of somewhere, engineers, say. And so V pi is just going to be the average reward by playing that policy. And then pi star is the policy among this collection that achieves the supremum of those policies. And you can assume that the policies are finite without loss generality, so the supremum is achieved. And what we're trying to do, we do not care about regret in this talk. What we're trying to do is we're trying to find a pi hat that is within epsilon of the optimal policy. Start a timer. And so some important quantities are going to be the suboptimality gap. So if V star h of s is the value if you start in state s at time h and then go on optimal policy, and q is the usual q function, this delta h FSA is just this suboptimality gap. Okay, it's the amount of suboptimality of deviating from the optimal policy on that step. Yes. Yes. Yeah. So we can assume that, like, it starts in a deterministic state, and then you transition from that stochastically. Yes. 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 Good observation. Okay. So what do we know about this problem? If we consider the full policy set, all policies are available to us now, so we can get the optimal policy. Ton is known about the minimax stem complexity. It's been an incredibly well-studied area going back years. And first, do I have a mouse? Oh, wow. OK. So and a lot of this work going back several years, almost a decade now, is trying to remove these lower order terms. Just again, this linear order terms of SH cubed over epsilon squared. It was very recently actually achieved, matching the lower bound. As a warning, in this talk, I don't care about H factors. I don't care about log factors. I don't care about lower order terms. They're all given in the papers, but just to keep this talk as simple and high level as possible, we're going to ignore those. So from a minimax complexity perspective, this problem is more or less solved. We have more or less matching upper and lower bounds in the worst case. And what worst case means here is give me any MDP with S states and A actions to find an epsilon good policy on the worst case MDP among these class of MDPs is no harder than the sample complexity. But I'm more interested in instance-dependent guarantees. So what happens if the MDP that you're playing against is an easy MDP, meaning these gaps, say, for instance, are very, very large. It's very clear to find what the optimal policy is. You should have a much better sample complexity. So, and these are called instance-dependent bounds, where the sample complexity is going to depend on more fine-grained attributes or properties of the MDP itself. So instance-dependent guarantees actually first appeared for regret, because regret is a more well-studied problem. And it was originally, Tuari and Bartlett had a paper, Ock et al. Had a paper. And really, this is just using change of measure arguments and then solving some non-convex optimization problem to get the optimal sort of policy asymptotically. And it was, it's optimal, but the complexity is just completely uninterpretable. It's non-convex optimization. You can't really use it. And so myself and Max Simchowitz in 2021 had the first paper that got a gap-dependent regret that has this sort of sum of inverse gap complexity that we're used to seeing in multi-arm bandits, right? In MIB, you usually see like a root kt or a sum over the inverse gaps times log t. Okay, this is that kind of result in that flavor. But we had some looseness in our bounds. Zhu et al. And Dan et al. Came back behind us and cleaned these results up quite nicely. And so this is the regret result. And of course, this is relevant because anytime I have a regret result, I can turn it into a pack result using the online to batch conversion. And so this immediately implies a pack result of this sample complexity right here. And this is immediately an instance-dependent result because those gaps are in there. If the gaps are very large, we get a better sample complexity. So I'm just going to summarize that idea into just a single bullet. We can achieve this regret bound. In 2022, my student, Andrew Wegemaker, and again, Max Simchowitz, again, these affiliations are actually old. He's now at Berkeley at the postdoc, and Max is now at CMU, assistant professor. But we achieved a sample complexity that looks like this. It is complicated. Let us decode this a little bit. So recall that WH mu SA is the state visitation of policy mu at time H being in state S and playing action A. Okay, so it's the state action visitation probabilities. Okay, and so what this infimum is the infimum over all policies. Okay, so these expiration policies of any type doesn't necessarily need to be within the policy set. They can be stochastic policies. It's an infimum over those, and we're not going to assume that we can reach every state, for instance. And now what's going on here is if you ignore this term for a moment, you just look at this term, then what's happening here is that basically tabular MDP is just a bunch of multivariate bandit problems, right? It's just in each state you're playing a different multivariate bandit. And so intuitively, the difficulty of identifying what the best policy is the difficulty of getting to every state and then just playing that multivariate bandit in that state. And then you can recurse backwards and solve every state and time. And so what this is saying if I can only get to a state with this probability, since infimum is a soup over this guy, so the easiest to get there, it's going to take at least the inverse of that to get there at least once. So that's sort of like the price of just getting there. And then you need to play the multivariate bandit problem, which is where this 1 over delta squared is showing up, just that typical sample complexity term. The significant bits here, it's minimax optimal, meaning this is never less than the bound above. And it's never less than that instance-dependent term above as well. And it's instant optimal as epsilon goes to 0, meaning if you're trying to do exact policy identification, you cannot improve upon this result. And again, this is the full caveats of I don't care about log factors, lower order terms, or factors of H. If this term's dominating? Yeah, it's bad. It can be, I mean, again, you're never worse than minimax. So you still have that guarantee, but like this is not necessarily small. This term shows up so we can recover the minimax result, but it can be suboptimal, which we'll see in a moment. No, it can't be. No, so if I just get rid of this term and I just use this term, that bound itself is never worse than the ASIH cubed over epsilon squared. So it's doing something. The second term there is what's allowing us to get the minimax result. So you might think, optimistically, that these regret bounds, these algorithms, UCBVI, all of these algorithms are getting really great regret. Maybe, they were never analyzed for PAC. Maybe they're right now just really great, and we just didn't do the right analysis on them. In fact, that's not true. So they're just an MDP with S states, and if you run any low regret algorithm, so any low regret, not just optimistic, but any algorithm that gets low regret, then the number of episodes that algorithm is going to need is 1 over epsilon, whereas this algorithm requires just order 1 samples, or order 1 episodes. Okay? So in terms of epsilon, I can make epsilon go as small as I want, and any low regret algorithm is going to have a sample complexity of at least 1 over epsilon. Our sample complexity is order 1. Okay? So regret and pack are fundamentally different for instance-dependent MDPs. Okay? In the minimax, there's no distinction. Optimism is great. In instance dependence, there's a fundamental gap. You need to do something different if you want to be optimal. Okay, but this brings up questions. How big is this term? How bad is it? You can come up with MDPs in which this is like clearly a stupid thing to do, or this is not necessary. And also, this Dan Marnoff and Murray paper in Zimmer, they introduced a gap. There's this notion of return gap. And they're really trying to make this point that like maybe just looking at the sum of inverse gaps for regret is not the whole story. There might be something more going on there because it's not really capturing the fact that like, well, if it's impossible to get to a state, you shouldn't have to pay for that, and things like that. And our algorithm really does try to get to every state. This algorithm is very much trying to get to the state and solve it, which is just not necessary. So we wanted to take a step back, and we started looking at, well, what if we just had a collection of policies pi? I think maybe the problem here is that this gap here, this delta HSA, which can be negative, can be positive, it's not the right notion that we should be thinking about. But what is, from a lower bound perspective, if you're trying to prove some change in measure argument, what you're going to get is actually something that depends on the gap in policies. So if V star is the optimal policy, or achieved by the optimal policy, this is the gap that we get between playing pi star versus pi. And what we achieved in this paper, so this was at Colt, this was at NeurIPS, and this paper was actually for linear MDPs. That's what it was designed for. But of course, linear MDPs are a strict generalization of tabular, so we can apply to the tabular setting to have a good story for this talk. And so it has these same terms, right? You still have this minimization over expiration policies mu, so you still have that inverse dependence just like here. But now what you have is this WH pi SA squared up here, and then you have this value gap down here. Okay, what's going on here? So one thing I think that is significant here is that these three approaches, these three ways of getting these results, require completely different algorithms. Optimism is, we all know optimism. This actual elimination is trying to get to every state and remove suboptimal actions. It's obsessed with trying to get rid of suboptimal actions. This paper, or this procedure, is really just trying to identify what are the worst policies, trying to figure out get a coarse estimate of every policy and get rid of the worst ones. Yes? Let's assume for the purpose of this talk that all policies start in a deterministic state, like S naught, and then they transition from there. No, sorry, maybe yeah, mu is often used as the initial state transition. That's not this. Mu is some expiration policy. It can be stochastic, yes. Excellent question, neither. There exist two sets of MDPs for which one is optimal and one is not. Neither one is optimal over the other, which is very, very upsetting when we figured this out. And you can imagine what these instances are. It's one that tries to make it very obvious that the policy is optimal, but getting an optimal action is hard, and vice versa. So what are we going to do? So I got obsessed with this problem, and I've been and thought about it for a long time, and finally I was actually at a Simon's workshop a couple years ago, and I saw a talk by Vivek, and he was looking at this double Q learning, thinking of this as an A/B testing problem over policies, and I realized, I'm like, wait a second, that's not the right estimator. Like, I think we can do something smarter, and this was sort of the result of this talk, anyways. So this is copied from the last slide. Define delta pi as the value gap and epsilon, the max of this thing, just for notational simplicity. And then that's going to allow me to make this a lot smaller into just that. Okay, so these two are the same thing. I've just made them a lot smaller. because unfortunately there's going to be a lot more terms coming in this slide. Okay, so this sample complexity that we had, we know it's not optimal based on the last slide, but like it still looks pretty good. And last year, Al-Majani et al. Proved a lower bound. So for the epsilon equals 0 case specifically, proved a lower bound that looks like this. And this paper was kind of like a good news paper. It was like, hey, look, you got something that was kind of close to optimal. And like, I would, it could be read that way. I was like, oh, devastated. It's loose. And so I knew it was loose already, but how bad is this? So if I applied W pi star up here and did triangle inequality, I could get something that kind of looks like this, with like a plus W pi star here. But we know that that's actually going to be quite large. And so I got obsessed with this problem, worked very hard, and we eventually got this sample complexity. So this is joint work with Adi and Narang, Andrew, Lillian Ratliff in ECE at UW, and myself. And this is like, we just submitted this in notes. OK, let's decode this thing. First, this term matches the lower bound. Fantastic. OK, so that's great. But then we have this other term. I don't know what this term is. It's very hard to interpret. It's for those that are like spidey senses, like, oh, that looks so familiar to me. Like if that square wasn't there, this is just a performance difference lemma. And you're like, oh, maybe that's what it is. Well, the absolute values here, if I just took that square away, it really does change it. It looks like the performance difference lemma, but I just can't relate them. If it was, that'd be phenomenal, because then this top thing would be delta pi, and you get 1 over delta pi squared. It'd be low order, and I'd get rid of it. But it's not. It's real. OK. So there's 3 main questions that you should be interested in, with the 0th order question being like, why do I care? This is just a complicated mess of math. And honestly, why you should care, we can argue whether tabular MDPs are a real problem that are in pressing need of good solutions. But for me, it's more about like, how do you optimally explore? What does optimal exploration look like? Sure, we can run optimism and get a minimax optimal algorithm, but like, given we are humans in this world, we want to find how to explore this world. What does that optimal exploration policy look like? What does that procedure look like? And that's what drives me in almost all my research. This is a conjecture of what it looks like, what you need to do. OK, so the first question is, this extra term, how does it relate to the lower bound? This extra term is not in the lower bound. Is it real or not? The second question is like, OK, so I've got this difference term as a lower bound, this upper bound. When is this like much smaller than this one? Is there any sort of gain there by looking at these differences over just this guy here? And then finally, what are the new ideas that actually get this? OK, let's jump in. So I'm going to call these 2 different terms. The first is the rewards term. The second is the transitions term. Why I'm calling it that is because, believe it or not, I can get that rewards term from a lower bound perspective. If you're doing hypothesis testing, I can get that rewards term by just perturbing the rewards. I don't need to touch the transitions. And if I just perturb the rewards, I can get that first term. Now, you can when you start moving transitions around, you will also get that term. But I can get that term with just rewards alone. And that's how Al-Majani got their bound, by the way. The second term comes from when I actually start perturbing the transitions. If I start moving them around, making it confusing about what future rewards will look like. That's really what this term is trying to capture here. And so like the first question is like, is this term real? It's still loose, right? Or it's not matching the lower bound, at least. Is it real? Yes, it's real. So there exists a class of instances such that the rewards term, which is the lower bound, is order 1, and the transitions term is 1 over epsilon, and any algorithm requires 1 over epsilon to solve this hypothesis test, which means that the lower bound is insufficient. There is this other term. I think it's that, but like I don't have a fully general lower bound stating that it is that term, but there is something missing in the lower bound. And this is what my best guess is the upper bound. Okay, but fear not. If there's a large class of MDPs, say a contextual bandit, this transition term is never greater than the rewards term. Okay, so and this is actually true for many MDPs, but obviously not all of them. And so in this case, like in the contextual bandits, our upper bound is actually meeting the lower bound. So sometimes this term is there, sometimes it's not. But in large classes of MDPs, it's not there, and we actually achieve the lower bound. Okay, second question. When is this actually much smaller than, let's say that second term doesn't exist. When is this much smaller than what Andrew's paper got before without the differences? And basically the answer is when it's easier to estimate the difference in the policies than it is to estimate the value itself. Right? Think about that. So like if I have to estimate the policy everywhere, I need to see where it goes, even to spaces that are just completely irrelevant in the MDP, I have to estimate what the value is. Because even if I know that that part of the MDP is irrelevant, meaning like I only have, say, 2 policies and they both agree on that set, I don't need to go over there. I know the policies are going to agree over there. But you still have to estimate the value of that policy. You have to go over there if you want to estimate the value. And so that's when these two terms are really different. And so a very quick example is if you just have 2 policies, pi star and pi, and they agree on all but one state, let's say, then this left-hand side can be just 1 over s squared times the right-hand side. Yeah, so it can be much smaller. And basically, this is the intuition here is exactly what I just said. If they agree on everything, you don't need to go everywhere to estimate what they're doing. I'll give you another example later. Doesn't matter. Okay, so now the ideas. Okay, perfect. The ideas here are, I want to identify epsilon good policy. How are we going to do this? So as v pi, I can write this value as just the, a big inner product or sum between state visitations and the reward function. Let's assume the rewards are known for now, just for simplicity. And I can. This is just the push forward measure of if I know what this is at h minus 1, I can push it forward to the h set by just using these transitions. And since I'm doing this online, I don't know what these transitions are. I'm going to be using some logging policy or expiration policy, and I'm going to use empirical estimates and just plug all this stuff in. And then I'm going to do argmax pi MLE. Okay, that's a reasonable thing to do. And if you look at the variance of this guy, it is scaling like it all comes down to these estimated state transitions. You get this, you apply Bernstein, and then you get this nice little quantity over here, which is just this ratio of w squared over w mu. And that immediately, well, not immediately, 60 pages later, and an elimination algorithm, you can get a sample complex that looks like this. But basically, that's the crux of the argument, is like, this is the true variance of this estimator under policy mu. Now you have to figure out how to do this infimum over all expiration policies and the max, and it's complicated, but you can do it. Okay. So we're getting more complicated now. Fix some policy pi bar, any policy. Fix policy pi bar, and just call this like a reference policy or something. And now what I want to do is I don't really care about estimating v pi. I care about the difference between v pi and v pi bar. Okay? I just want to know, relative to pi bar, how is v pi doing? And if you can write this down. If you define this delta h pi of s as being equal to this thing, which is just the difference in state visitations, okay? It's just the probability of pi being in state s or pi bar being in state s, it's just a difference of those. And by just doing some simple algebra, this equation is true. Okay? I define this delta, and using that definition, the above statement is true. And just like the above, I can define this thing recursively. I can track just the differences. Basically, where are these policies actually differing in the MDP? and I can track this thing, and I don't know these quantities, so I just put hats on everything and do this empirically. I roll out pi bar independently and just get the Monte Carlo estimate of it. And then I'm going to call pi hat VR to just be the argmax of d hat pi. Okay? And if you do that same sort of analysis, like, OK, I'm going to do Bernstein and simplify, if you do that, you get exactly this term, this differences term, and this performance difference lemma looking term. And 60 pages later, you can get this sample complexity. Okay? And so this is really where it's coming from. It's not so magical. It's really coming from just trying to split up the difficulty of estimating where pi bar goes, right? This is the difficulty. Where is pi bar going? I just need to estimate that. But I only need to estimate it once for one pi bar. And then all I need to track is how every other pi relates to pi bar, which can be very low variance. And so, of course, if you can estimate these quantities with an epsilon, you get epsilon optimal policy. The difference that the variance of v hat pi scales with this guy, the w hat pi of SA squared, whereas this one, it only scales with the variance of deltas, and that's the differences. Okay? Why does this matter? This matters because this guy is a probability distribution. It has to sum to 1, meaning it has to be big somewhere. Okay? This guy doesn't. This guy is a difference of two probability measures. So if they're almost equal to each other everywhere, then this term is going to be very, very small. Okay? And so, in fact, you can show that this variance, estimating that v pi, always requires 1 over epsilon squared, like necessarily. It's the minimax rate. But you can actually estimate d pi in 1 over epsilon episodes. This is the gain. It's getting this extra variance reduction by looking at the difference of policies versus the policy itself. The algorithm is this. OK, the algorithm is actually 3 pages long. But this is the simplified version. The difficult parts are doing this minimization over mu. This is hard. You don't know where your exploration policies go. So you need to figure that out. You need to sort of map your MDP out to see where they go so that you can even do this optimization problem and find out what is the best one. Then you need to estimate the W hat pi's. You need to estimate the Q hats. It's all, there's a lot of estimation going on here. But fundamentally, this is I really do believe that this is the right sample complexity. And so my conjecture is actually that this is tight. I really do believe that this second term is real. It's there and unavoidable. But I couldn't prove it in general. So that's my open problem. Also, what about regret? We know we don't have necessarily the right upper bounds and lower bounds for the full policy set. For a restricted policy set, I don't know anything. I don't know what the minimax rate is. And so that's it. Thank you. In what sense asymptotic? So this is a good question. So what is known is basically Lyon-Robbins style lower bounds. And so Andrew and Dylan Foster had a paper recently that had finite time results for regret, and that include MDPs. But in all these results, like Ock et al. And Bartlett and Tuar, basically they're solutions to these non-convex optimization problems that you have to solve. And yes, they match asymptotically, but it's not clear what they are. It's not clear what are the real terms. It doesn't really tell you anything about how to explore or what these terms are. If I change the MDP, would this get easier? But they're not interpretable. That's true as well, yes. Yeah, so I'm not really caring about burn-in times in this work because I'm going to low order. But yeah, that's a significantly difficult problem. Getting those low order terms is very hard. So like, yeah, for there's definitely asymptotic results known. You can find it. Yeah. Well, I mean, it's this term that is turning into this term. And I mean, this is a zero mean random variable. And so why this square is coming up is because I'm just, if you just compute the variance of this term, that's where it shows up. I mean, like, honestly, I've looked at this a lot. I don't know. If someone in the audience sees this numerator here and like something clicks and it makes sense to you, I'd love to hear about it. Because I tried to relate it to different quantities that I know about, and I couldn't do it. But it seems fundamental. I just don't recognize it. Cool. Thank you.